All right, then without further ado, we have Filippo Revello, and he will tell us about string theory in the first half of the universe. Take it away.
Okay, so first of all, let me also thank the organizers, both the old and the new ones. And today I'm going to be talking about the string theory and the first half of the universe. This is based on a paper that came out today, together with Fee Napers, Joe Conlon, Ed Copeland, and Martin Mosny. And I'm also going to refer to some another paper that I put out on the archive a few months ago in November. Now, to compensate for a very string talk, this talk will actually be very fino, so be prepared. As you might imagine from the title, the setting here is going to be string cosmology. So this is a talk on string cosmology, but string cosmology with a twist. And the twist consists in the following fact. Usually, whenever people try to do string cosmology, they start from something, for example, some desired epoch in our universe, some desired feature that we'd like to observe, and then they try to embed it into string theory. And in practice, for many of the things that we would like to have, so for example, inflation, cosmological constant, or accelerated expansion more in general, this turns out to be very hard. So one might wonder whether these things might be possible in string theory, but only if we go beyond what we actually know. So for example, if you go beyond the perturbator lamppost. So in the meantime, while we resolve these things, I think it's also worthwhile to ask, what happens if you try to approach this question in reverse, and rather than starting from, what you would like to embed in string theory, you start from the string theory side, and you ask, what are the most common cosmological behaviors that we think are compatible with what we know about perturbator string theory, for example. Now, by this, I do not mean at all that one should not think about inflation or accelerated expansion, of course, since this is what we observe, it's crucial, but I think this is sort of a complementary perspective of something, with the string theory that we do know right now, is there anything else that we can say about the evolution of our universe? And very generically, what I'll try to argue is that the same features that make some of the things that we would like to have very hard, so for example, the very steep potentials that characterize string theory make quintessence very hard to obtain, very accelerated expansion very hard to obtain, the same features point towards the fact that maybe string theory generically is characterized by cosmological epochs where one has a different behavior. So for example, kination, where scalar fields are rolling very rapidly down a steep potential, or for example, the so-called trackers, which is something that I will introduce later on, and they're essentially situations where the energy density is co-dominated by various components, including scalar fields, matter, radiation, and so on. And finally, in the last part, I'll try to ask whether there is any observable consequences from this, and whether we can, really try to get closer to testing string theory with observations. Now, complementary motivation is also provided by cosmology, because there is if you look at the history of the universe on a log scale, which is somehow arbitrary, but events tend to be very dense towards the beginning, you might see that there is a very large region which is unconstrained essentially by observation, and this is essentially between the end of inflation and the onset of BBN. And this region is not transparent to photons, so we don't really have much clue of what is going on there. People usually assume that you have a long epoch of radiation domination, but again, it hasn't been tested really. And this territory, I think, is really a huge opportunity for string theory, because first of all, well, it's unexplored from a point of view of experiments, but secondly, it's also really string theory territory from a more theoretical point of view, in the sense that these epochs usually involve very high energy scales, perhaps the closest we can get to stringy energy scales. If you're optimistic and assume that inflation happens at the gut scale, this will be something on gut scale or a bit lower. And also, some of these epochs, such as kination or trackers, which I will introduce right now, are actually characterized by trans-Planckian field displacements. And now this is something that you can only try to deal with if you are in a UV-complete theory of quantum gravity, such as string theory. Otherwise, you can't really, even then you might have some problems with this one-point distance conjecture and so on. So this is really, it's really string theory territory, and it's really unconstrained. So something interesting to look at. So after this motivation, let me just briefly give a short plan of the talk. So in the first part, I will introduce these exotic epochs I've been talking about. So tracker, kination epochs, and all that. Then in the second part, I will discuss some implications, and in particular put forward a sort of benchmark scenario and show some calculations that we did on the cosmological perturbations and possible observations. And finally, I will present an outlook and mention some potential signatures, but still at a very qualitative level. So let's begin, part one. Now the first, I will try to treat this a bit more generally in the following, but the first easy example of a sort of non-standard cosmological epoch, which could be, relevant in string theory is that of kination. So kination is essentially when a scalar field is rolling down a steep potential very fast, such that essentially the opposite limit to lower inflation. So in this case, the kinetic energy is dominating over the potential rather than vice versa. So this is also known as a stiff fluid sometimes. And if you assume that the kinetic energy is actually dominating, then you can solve the equations of motion. It's very simple, and you get something like this, or phi evolves logarithmically in time, or in conformal time. And now the one thing to notice here is that there is a big m Planck factor sitting in front of this logarithm here. So every Hubble time, roughly speaking, your field will evolve a distance that is Planckian, or roughly. And another point of view on this kination business provided by the fact that this is something we wrote up in a paper last year. If you assume that this kinating field, if you identify it, which we will do with the volume modulus of some compactification, so the overall volume model of some string compactification, then you can also uplift the solution to a 10D Kastner solution, which is, I think, quite interesting. But I won't really have much time to talk about this. It's just to flesh this out. Now, why can kination be relevant for a universe? One thing about kination is that its energy density redshifts very quickly, as 8 to the minus 6. So if you have any other sources present, if you have matter or radiation, this gets very quickly washed out. So the only place essentially where you could, one of the few places where you could be thinking about kination is after inflation, where all of the other sources have been diluted. It's one of the few opportunities for these fields to start rolling down these potentials very quickly. And also, again, this is very generic. String theory potentials, at least in the regimes where we can compute them, are also often very steep. For example, if you look close to boundaries of moduli space, a lot of work has been done also by some of the organizers here. And so this is sort of the generic motivation. So what you can have in mind is a situation like the one depicted in this figure, where you have a potential that is like the red curve shown here, which has a very steep part towards the left, and then it goes down, there's a minimum, and this minimum is separated from decompactification essentially by a very small barrier. And if you want a specific example, you can take this to be the LBS potential for the volume modulus. So a compactification where all the moduli are stabilized by fluxes and a combination of perturbatory and non-perturbatory effects. And you only have one light field, which is the volume, which has a potential which is at exactly this form. And in LBS in particular, since this field is the volume, this is rather special. Starting out from the very left of this plot is something that you actually might expect, because if you want inflation to happen at a high scale, then the string scale cannot be too low. And low, the string scale is roughly 1 over square root of v. So you want to be on the left-hand side. Now, one thing to, okay, this is a kination. Now, I'm going to introduce now these other epochs that I was talking about, these tracker epochs. And a way to introduce them is actually a practical problem that one encounters when dealing with kination. That is, if you look at this plot here, you might imagine that if you start rolling very quickly down this potential, especially if this barrier is very shallow, you might overshoot and end up to decompactification. Now, this is actually not the case, because as I was mentioning, if you have any other source of matter or radiation present, this will catch up very quickly because it redshifts in a much slower rate. And in particular, if your potential is a simple exponential, then the equations of motion can be solved quite simply. And you can see that a system of this kind will start with kination, and then as long as you roll down this exponential potential, you'll reach this unattractor solution, which is characterized by constant energy densities. So energy density which are all in order 1 ratios to each other. So a solution where you have order 1 energy density in radiation, order 1 energy density in the kinetic energy of the field, and order 1 energy density of the potential field. And these are so-called tracker solutions because the behavior of the field is tracking that of the fluid that is it's put with, in this case, radiation. And this can actually be done more in general, and I will be say a few words now about what can be done in perhaps a more stringy context. So a scenario I have in mind is where you have your typical EFT coming down from string theory, so an n=1 theory with some current multiplets, where I've denoted here the saxions in orange and the axions in yellow. And you can do the usual thing. This isn't just I'm sure you're all familiar with this, it's just set denotation, but you have some scalar potential. And in particular, there are regions where these things can be computed, for example, close to boundaries of moduli space. These things get, they will have a very sort of an easy form. And in particular, if you can write down a Kähler metric of this form, or as happens in all asymptotic limits of moduli space, and if you neglect corrections, then you have a situation of this sort, where the potential is exponential in the canonical normalized fields. And in this case, you can solve the equations of motions exactly, or I mean, you can at least analyze them analytically and find out what the attractors and repellers are of the system. And this is because, and this is something that goes back to a long time, the equation of motion of cosmology can actually be rephrased as a dynamical system of the first order. This is something that has been known for a long time, but it's been also recently used in the context of scalar field cosmologies and bounds on accelerated expansion, the works of Gary Hsu, Tonioni, and Tran, for example. And you can actually include axions in this setting as well. So this is what happens if you have axions, saxions, and just exponential potentials. And so the axions here again are orange, the axions are yellow, and this red is some sort of cosmological fluid. But basically, in this situation, if the potential takes a simple exponential form, you see that you can write equations where this is a first-order autonomous system. So on the right-hand side, nothing depends on time, which is denoted here by m. And then you can solve for the average the right-hand side of this equation to be 0, and you can find critical points and see what the attractor solutions of the system are, and then compute them. And so in particular, these are what I would be calling tracker solutions. And there exist various kinds. The famous, the first ones are the ones that I discussed at the beginning, the ones that allowed you not to overshoot. These are matter radiation trackers, where essentially kinetic energies sub x, the kinetic energies of the scalar field, and the energy in radiation. At one point, they go to order 1 constant value, relative value. And this will be relevant for the rest of the talk. You can also have similar solutions with axions. So some of them, the first paper, there was a paper dealing with these solutions by Michele Ciccoli, Di Bitetto, and Pedro in 2020, which also somehow, I don't want to enter this rabbit hole, but somehow if you have systems of this kind, you can find attractors that give accelerated expansion if you have a lot of field space curvature, so which is a big caveat. And also in this recent paper that I put out in the arXiv in November, I classified these solutions for an arbitrary number of axions and saxions, and looked at examples in, for example, asymptotic limits of boundary space. But there, for example, you can never find accelerated expansion. But the thing that would be relevant for this talk would be the trackers on the left-hand side, because for whether the kind of solution that you have really depend on the order 1 values that the specific couplings take. And so in a realistic model such as LVS, which is what we will consider for the more second part of the talk, you can only have solutions of this kind. So the axions will never play a role, and whenever you start rolling down the exponential potential in LVS, which has a very specific form, whether the exponent is some order square root of 27.5, so a fixed number, in that case, you will eventually always end up in a matter or radiation tracker. And so this is the end of the first part, where I introduce all the ingredients. I don't know if I should take any questions here, or maybe just at the end. So this is the second part again, so on implications of phenomenological implications of what I've been saying. So what I want to do here is really take precise and definite example of a full-fledged cosmological history that starts at the end of inflation and ends at the beginning of BBN. And because some of these tracker solutions or some of these cosmological solutions have received intermittent attention in the literature in past years, but with different aims, for example, for dark energy, but there's never really been an attempt to try and piece all these things together to give a coherent evolution from the end of inflation up to, well, nowadays. And this is what we try to do. So what we have in mind is a cartoon like the slide shown here, where you start at very high energies and then you have inflation. After inflation, some scalar field, which for our purposes will be the volume field in LVS, starts rolling down and along this very steep potential. And then again, if there is any matter or radiation present, which in a realistic universe there will be, then this kination solution gets attracted to a tracker solution, first for a phase of radiation domination, and then it goes to the tracker. And then finally, as you go more towards on the right-hand side, the field will start to approach the minimum of the potential, which is shown here, and very small compared to the other scales shown on the plot, start oscillating around the potential, and then eventually give rise to modular domination and reheating. And now in the slide, in this picture, the inflaton is shown to be the same as the volume modulus, so as the same as the field giving rise to all these non-trivial dynamics, but this is just for convenience and just to have a 1D picture. But in general, we don't really make any assumptions on the nature of inflation. you can imagine to have an inflation of any different kind, but the only thing that you want is that requires that at the beginning of the evolution, the volume modulus is sitting very high up along its potential, and then it starts rolling. And so as I was saying, the first thing we did is actually, and you can find the details in the paper, was to really characterize this cosmology and all of these various epochs in a quantitative way and piecing all these things together. Now, this is quite standard stuff. The only thing that, one thing that is non-trivial is that, however, we have to describe all of these epochs, and also there's some transients going in between. So we also gave some analytical treatment of all these transient epochs. For example, how you go from kination to radiation domination, and you can write down analytical expressions. And now, the precise form of this is not very important, but when we want to go to the next step, that is compute cosmological perturbations over this background, then it will be very useful to have these analytical expressions. And then the main thing that we focused on is cosmological perturbations. So cosmological perturbations are really telling you how the initial fluctuations arising from inflation have propagated up to the current day to become what we observe in the universe, and structure would range from galaxies to galaxy clusters and so on. Now, of course, this is a very messy and astrophysical subject. So because at some point during the evolution of the universe, these perturbations become nonlinear, and then you have to use simulations and so on. So what we did here is just investigate how these perturbations grow within an initial slice of time evolution during the evolution of the universe, and as long as these perturbations remain linear. And to do so, essentially, you just have to take the Einstein equations, plug in an ansatz for the most general metric that you want, compatible with certain principles, isotropy, etc. And then also plug in an ansatz for the stress energy tensor, and then solve these equations in perturbation theory. Now, of course, this is a GR, so you have some gauge invariance, and you can play various tricks. And for example, it's very convenient to express the metric in this form here. This is known as the Newtonian gauge, because if you take the relativistic limit, this is really essentially GR is essentially classical relativity, where you have some with this field phi, this really describes your gravitational potential, and so I will call this variable phi the gravitational potential. And also you can do the same, expand the stress energy tensor depending on what matter content you have. So here we'll have a scalar field plus some unspecified fluids, and then you can plug this into the Einstein equation and solve these equations. Now again, this is a GR, so you have to look at the results. You have to be careful about gauge spurious modes, and so we're using the right variables. So for the purpose of this talk, the one thing to keep in mind is that there will be one variable which is called big phi, which is the one appearing in this Newtonian gauge in this form of the metric, which is also a gauge invariant variable, turns out, if you define it in the proper way. And also, so this will essentially, it will describe the fluctuations in the gravitational field. So whether, at some points you get dips where matter can start to accumulate, and then you have structure formation. And also we have this delta, where delta is essentially the density fluctuations normalized to the average density plus some correction. And this correction is only to make sure that this quantity delta is gauge invariant. But you can really think of this, especially on small scales, this really reduces to your density fluctuations. And so now these are this table here. You can see some standard results that you can derive for what we know are standard epochs in cosmology, radiation, matter domination, and so forth. And what we did was to try to apply this same formalism to compute these perturbations in the case of all these various epochs. So I will not spend much on these technical details, but essentially what you have to do is solve these perturbed Einstein equations, which take this form, plus the equations of motion for the scalar fields that you have in the system. Now, this is quite ugly, so I won't really dwell much on the details, but usually you can simplify. The thing you really care about are the sub-horizon and the super-horizon behavior, and in these limits, usually you can simplify things quite a bit. And so here are, roughly speaking, the results. So what we found is that during kination epochs, for example, the behavior of perturbations growth is very different from that of radiation domination or matter domination epochs. In particular, in both super-horizon and sub-horizon scales, perturbation growth is enhanced quite dramatically. So it goes as 8 to the 4 in super-horizon scale, and it goes in A of beta times some oscillating factor in the sub-horizon limit, where this 8 of beta is the scale factor. And this is faster both than radiation or matter perturbations during both matter radiation dominated epochs. So this, if we really had kination in our universe, you would really be able to see, well, not to see, but you had this anomalous growth of perturbations very early on. And this could lead, for example, to the production of primordial black holes. And this is maybe something I'll mention a bit later. Now, during trackers, the situation is a bit different. For a radiation tracker, this is actually very similar to when you have radiation domination. So there's only order 1 differences which arise. And instead of having oscillations of a certain kind, this is just a sub-horizon limit. You essentially get superposition of 2 oscillations with different order 1 factors, but this is quite similar. What is interesting is that in the matter tracker, so if you start down kinating, and then there is a very small amount of matter present, and then this amount of matter grows relative to kinate, to the kinating field, and becomes to dominate. In this case, on the matter tracker, you have an anomalous growth of perturbation again, which is depends on the specific value of the exponent in the potential, which is this lambda indicated here. So if you were very hypothetically be able to measure this, you might be able to say what kind of potential we live on, for example. And again, it's slightly enhanced with respect to the case of matter domination. For example, if you plug in the specific value of lambda corresponding to the LVS potential, you get this number shown here. And also we did the same analysis for various transiting epochs, and these result in very complicated and ugly expressions, so I will not put them here. But we also have some analytic expressions, not in all cases, for those epochs. And so what you might wonder at this point is whether this can be of any use for phenomenology. Now, in theory, these perturbations are observable quantities, but the problem is that since the scales we are dealing with are very high energies, corresponding to very small length, in astrophysical terms, these correspond to perturbations which are on the, for example, galaxy scale or similar. So these are really very messy astrophysical environments where things get nonlinear. You have to take into account a lot of effects, and it's really difficult to say something. So the one thing we might wonder is whether any of these weird cosmologies might give rise to any other implications in particle physics or cosmology. Now, this is something that we didn't really spend too much time on. We only flashed out as a hypothetical and just a qualitative possibility. So I'll mention them very briefly. One idea is that, again, when you have time-dependent scalar fields, in string theory, this means that you have time-dependent, for example, couplings, because these depends on the VEV of the scalar field. So, for example, you might imagine to have time-dependent couplings, or in the case of LVS, if the volume modulus is the one that is moving around, that is kinating, or that is tracking, in that case, you might have a time-dependent string scale. And another thing that you might have is that, again, this epoch gives it enables you to have very large dilution factors, which can be relevant, for example, for dark matter or baryogenesis. And finally, before I conclude, I would like to mention just one other possible signature, which is perhaps the most promising one and the most direct, is that instead looking at for gravitational waves. This is because essentially the reason why we don't know much about the universe before BPN, because the universe so early on is not transparent to photons. So the only thing that gets to us that we could in principle see, whether we can do it in practice is another question, are gravitational waves. And so, for example, it's a known fact that if you have an epoch with a modified equation of state, for example, kination, it could result in a peak in the spectrum of gravitational waves. And for example, if you take the standard inflationary spectrum and propagate it through an epoch of kination, this gives us a peak in the observed spectrum of gravitational waves. Now, this has been studied in some BSM models, but in our case, it's not particularly relevant because this would be a very high frequencies, which we cannot observe yet, and probably not even in the near future. However, one possibility that I think is interesting is to look at, for example, the instead gravitational waves emitted from a network of fundamental strings. And this is for two reasons. Well, first of all, we are doing string cosmology, so we can really assume that such a network of fundamental string might exist. And secondly, although this, in the standard vanilla scenarios, there is very stringent bound on the amplitude of these gravitational waves, which put very low bounds on the string scale. If you have a scenario like LVS, where the volume evolves through a trans-Planckian field distance, you might well have a situation where after inflation, the string scale is quite high, but then when these gravitational waves are emitted just before the CMB, then the string scale is lowered significantly. And so this could be still compatible with some observed signals. And moreover, in this case, you would have time-dependent string tension, for example. This would give rise to a very unique and very stringy signature if you were able to observe this. So I would like to conclude with an outlook and future directions. Again, I think there is one main message in this talk, which is that these exotic epochs from string theory are, I think, well motivated. They really are string theory territory in the sense that they cannot be described with an EFT, but you really need to know string theory to know how these behave. And I've mentioned kination and truncated epochs. And this is really a vast and unexplored territory for phenomenology. There is a lot of things that I was mentioned briefly at the end that I think have a lot of potential. For example, gravitational waves, primordial black holes, time-dependent couplings, anomalous growth of perturbations, dark matter, radiation seeds and scalar self perturbations, or even things with axioms. And so I think it's something that has been neglected so far in the string cosmo literature, but appears to be a very promising direction. And my 25 minutes are over, so thank you for your attention.
Thank you, Filippo. Are there any questions from the audience? Let me quickly ask one before they come in then. So in these scenarios you lay out, what do you precisely, like, is there a specific type of Calabi-Yau? Like, would it work for any, or do you need to assume some properties there, or kind of fluxes you need to turn on, these sort of things? Or does it work for anything in a large volume scenario, this sort of thing?
Well, I guess it depends on what scenario you mean, right? If you want to do LVS, then yeah, you require a Calabi-Yau that has the properties that the large volume scenario requires, but nothing more. So you want something like a Swiss cheese Calabi-Yau, where you have one large cycle controlling the volume of the manifold, and some blow-up cycle, which will some small blow-up cycle, which will allow you to stabilize all the moduli as in LVS. But there's no further assumptions.
I see.
If you want to think about, again, you can also think of kination or exotic epochs in more general context, for example, and asymptotic limits, and it's less precise what the evolution would be also with regards to, we also have to take into account modular stabilization. So I'm not sure if you can already think of these as complete scenarios, but I think the fact that you have C potential is generic and does not really depend on any properties of the manifold.
Thanks. Any further questions? Pavlo?
Hi. So thank you very much for the nice talk. I just wanted to understand a little bit better, like the motivation at the beginning, like in the sense of when you kind of explain this as trying to shift things around and starting from string theory and obtaining all this and somehow it being natural and so on in string theory to get these things. I was wondering, like, in this regard, how generic are you claiming, or do you have any idea on how generic this should be in the landscape according to what you are seeing here? Or, are you somehow claiming genericity of these kind of scenarios in string theory, or just that the ingredients separately are generic, but then maybe combined they are less generic? Or is there any big claim regarding this in
No, regarding this, there is no big claim. I would say that I think it's a bit tricky because I think before you want to start to do any pheno at all, you would like to stabilize the moduli. So we just haven't got that many different scenarios. All the moduli are stabilized under control. So in LVS, you can do it, and then you can see that things work out. But so in general, no. In general, it's, I think, as you were saying in the second part of the question, so that some ingredients are generic, for example, C potentials. But then, for example, you also need to justify why during the evolution you start at some point which is high up along this potential. But then again, this is also all of this assumes that at some point this potential also has a minimum which it will stabilize into, maybe at a Sitter minimum. So of course, there's many ingredients that you need to involve, and depending on what you mean by generic.
Right.
For sure, more generic than things like quintessence or accelerated expansion.
Yeah. All right. Thank you.
Marco?
Hello. Hi, Filippo. Nice talk. I have a question regarding the. Can you hear me?
Yeah.
Yeah, regarding the the perturbation. So you show that during kination there are different behavior perturbation. It's not clear to me because it's not clear to me how this change of perturbation behavior will affect later evolution of the cosmos after reheating, because I guess this kination period is before reheating, right?
Yes. So yeah, you're right. Well, a general problem of this is that these perturbations, if one were to hope to observe them, they would generically always have the risk of being washed out by reheating. So one place that would be relevant, I think, is mostly indirect. So for example, you can imagine a situation where the scalar field kinates, and then these perturbations grow, and they grow in such a way that you can form, for example, primordial black holes. Then these primordial black holes maybe give some gravitational wave signature, which you can observe, and then the rest of the perturbations are washed out by reheating, but you can forget about them. So maybe this is one way. Otherwise, I agree but it also would depend on the details of reheating, I guess, if these perturbations are washed out or not.
But in general, I would expect that the effects are not a large scale, but a small scale, right?
Yes.
Because it's this kination is happening after inflation, right? Before,
Yes.
between the end of inflation and the reheating, if I understand correctly, the picture you have in mind.
Yes, I agree. So yeah, that's why I would say that observing these directly is probably quite impossible, but maybe there can be indirect effects, these perturbations, such as but primordial black holes.
I know it's the paper today, but I haven't had the time to go through it. But and I was thinking that maybe you guys discussed these kind of things.
Yeah, I think it's hard to. Yeah.
Okay. Thank you.
If there are no further questions, let's thank both speakers, Filippo and Hamza, for their talks today. And then we can close the recording and keep the session maybe a little bit longer online if people want to discuss.